The other hyperparameter or the other concept in deep learning that we should know is learning rate. Do you remember the back propagation, by the way? The back propagation algorithm. What do we do in back propagation? Overall, what are the steps? Let us think about them. What are the steps? You have the input layer, right? You have the hidden layer or hidden layers. Okay. To keep it simple, I'm taking only two hidden layers. Then you have the output layer. Then tell me what are the steps to find these weights? What steps that we follow to find all these weights? What steps do we follow? Do you remember that whole? I don't know the weights in the beginning. Initially, what do we do? Initially, what do we do with these weights? What is the first step? Do you remember the first step? The initial step is randomly initialize the weights. That means some random weights can be given to them. Later on, we will take the right weights. Random initialization. Okay. After that, what is the step? Okay, random initialization, not a great deal. What is the next step? You take the data and make the calculations forward. That particular step is known as, what is the name of that step? Feed forward step, right? Feed forward. After feed forward, what do? We do the calculations forward. Then you have all the y predicted values. Then you already have the y actual values. And what do we do? Usually when you have y predicted, y actual values, after the feed forward step, what is the next step? Error calculation. We calculate the error. After calculating the error at the output layer, we have to do one more step. Within this one, there is one more sub step. Right after calculating the error at the output layer, what do? What is the next step? We find the error contributions at each of these hidden layers. That step is known as back propagation step. Now I'm talking about the last step. Once you have the back propagation done, once you have the error at this particular node, error at this particular node, error at this particular node, what is the next step that you're going to do? What is the next step? You do the weight updating or the weight adjustment. I'm going to talk about this one now. Weight adjustment. How do you update the weights? Weight new equal to old weight. Yes or no? Weight old plus some delta W, some weight, you have to move it. That means you may have to increase the weight, you may have to reduce the weight. You will move in that direction where overall error reduces at this particular point. Error reduces at this node, error reduces at this node. We have to make that adjustment, maybe positive adjustment, maybe negative adjustment. Positive adjustment means we may have to add the weight. Maybe if your initialization is lower, then you may have to increase the weight. If your initialization is too high, you may have to reduce the weight. But there is a small twist there. This is the original weight updating formula, where weight equal to weight old, that means weight new, equal to weight old plus some weight adjustment. Instead of adjusting as it is, whatever is the weight adjustment, we multiply them with some parameter called eta, which is known as learning rate. That means instead of updating the weight based on the formula, I am multiplying them with eta, learning rate. Maybe usually eta is set to be between 0.001 to 0.1 usually. Or maybe we can say learning rate can be any value. It can take any value, but usually while we are dealing with the networks, we will set it as a value between 0.001 to 1. By doing so, what are we doing? Let's say weight adjustment suggested is, let's say 20 is the weight adjustment suggested originally. But if I set learning rate equal to 0.1, how much weight change that I'll do? Tell me finally. 20 is from the formula. But if I set learning rate equal to 0.1, how much weight adjustment that I'll do? Since 20 is the suggested one, we will do eta into 20. So we will do the weight adjustment of 2 only. This learning rate is in our hand. You know what we want to do? The weights are changing. The weights are changing from epoch to epoch, from here to here. This is the error function. On the error function, the error will reduce based on the weight change, like this. The weights are changing. We want to take control of that weight change as well. We want to take that matter into our hands. We want to dictate the way the weights are changing. If learning rate eta is too low, tell me what will happen? Weights will change rapidly or weights will change slowly. If it is too low, if eta, if I set it to be 0.0001, what will happen? Think about it. If I set this learning rate to be too low, the weights will change rapidly, or the weights will change minutely or very slowly. If the weights are changing very small, what will happen to error reduction? Will it reduce rapidly, or error reduction will happen very slowly? If weights are hardly any, if you see any change, hardly any change in the weights, error will also converge slowly only. Algorithm will also get slowly. Algorithm will also converge slowly. So eta, if eta is too low, then weights will change too slowly. If eta is too high, if eta is too high, what will happen? Eta is too high. Let us suppose if I kept eta equal to 2. We usually don't do that. If the weight change suggested is 20, if I say eta equal to 2, that means I'm changing 40. Then we will be changing very fast. Remember, too fast is also a problem, too low is also a problem. I'll tell you why. Look at this. Let us suppose if weights are changing very much rapidly. First of all, why learning rate is required? Why are we taking the weight changing matter into our hand? Why can't we leave it as it is? If you leave it as it is, there is one big issue called local minima, getting stuck in the local minima. Let us see what is that problem of getting stuck within the local minima. Here is the problem. Let us suppose this particular curve that you see, that is the error function. Look at this, all of you. This is the error function. Imagine that with the random initialization of the weights, you have started here. Later, you entered here. Later, you entered here. Now, listen to me carefully. Now, what algorithm thinks is, okay, I have reached the global minima. There is nothing below this. I have reached the global minima. The algorithm will exit here. Why it is exiting? If you ask the question, why are you exiting? It will say, if I go to next iteration, I am seeing a higher error. I think seeing higher error is not a good idea for you. I have reached the lower error. I have exit like this. And this is a problem with all the deep neural network problems. With all the deep neural network problems that you are going to solve, the issue here is you will get stuck in a local minima. Do you understand what is local minima for any complex function? Okay, there are local minimas and global minimas. Global minima is only unique. Only one global minima will be there, or there can be multiple global minimas as well. Usually global minima is unique. Local minimas, you can have multiple local minima. This is local minima. This is local minima. Yes or no? This is local minima. Like this. Now, listen to me carefully. What is the issue of global minima and local minima? So, your error function is kind of very complex. We can't even see that actually. Let me draw it slightly better. Your error function is very complex. It's like this. Maybe with random initialized weights, during the algorithm, maybe once your overall solution, if it gets stuck here, then it will be difficult for it to push it out of local minima. You can somehow push it out of local minima by changing the way the weights are moving. Maybe you can jump over this local minima by choosing the right optimal learning rate. If you choose a lower learning rate, think about it. If you choose a lower learning rate, weights will move slowly. If you are choosing lower learning rate, if weights are moving slowly, do you agree with the point that you may have higher chance of getting stuck in the local minima or not? If my weights are moving slowly, then we may have the chance of getting stuck in the local minima. If somehow we change the way, oops, somehow if we change the way the weights are moving, that means if the weights originally have to move by this much, if I somehow change the way, somehow if we push it out of the local minima, that means by choosing the right step size, that means you can imagine that this is a kind of step size in the sense like how far you are jumping on the overall error. Somehow we want to at least push out of this local minimas. I'm not saying we will definitely always fall into the global minima. If we are at least nearby the global minima, we can get still stuck in the local minima, but if that is nearby the global minima, we are still good. That means if overall accuracy is 93% possible, if we are somewhere getting 92% or 92.5%, we are still fine with that. However, if we are getting the accuracy of 70% or 80%, that means somewhere in the local minima we got stuck. How do you avoid getting falling into the local minima? You can avoid falling into the local minima by choosing the right learning rate, by changing the way the weights are changing. Instead of saying from here to here, I would say I would choose a slightly larger learning rate. After this it will fall here, after this it will come here, after this it will come here. Or maybe if you're starting here, if your learning rate is lower, you may get stuck here. To avoid it, from here to here, after that here to here, after that here to here, and then here. Maybe if you are here, somehow to avoid it. Can you really see this error graph? Tell me, can you really see this? Can you draw the error graph and see for that much multiple, almost like 5,000 weights are there? Can we see it? We cannot see it. That is why we need to work with the learning rate. Now there are two problems. If the learning rate is too high, think about it. If the learning rate is too high, that is also a problem. Low learning rate, you understood the problem. If the learning rate is too low, what is the problem? Can somebody tell me? We already discussed it until now. If the learning rate is too low, what is the problem that you see? Immediate problem. If the learning rate too low. If the learning rate is too low, the weights are changing slowly, the error reduction will happen slowly. That is one point. What is the bigger issue here? If the learning rate is too low, getting stuck in the local minima, that is the point that I want to convey. You may get stuck in the local minima. Now, that doesn't mean learning rate has to be always very high. If the learning rate is too high, let us see whether you can guess that as well. Learning rate is too high. After here, you fall here. After here, you fall here. After here, you fall here. The step size is so high, you'll move in between them. Can you tell me what is the issue if the learning rate is too high? What will happen? What do you see here? What issue that you see here if the learning rate is too high? We might even miss the global minima because the step size is so large that this doesn't have the scope to enter this. Do you agree with that point? At every point of time, you have to take such large steps that from here to here, here to here, your algorithm will oscillate. After a point of time, it will oscillate between these 2 points. It will never reduce the error. So learning rate too high. Think about it, all of you. If the learning rate is too high, that means your step size is so high. That means your weights are changing so rapidly that they cannot even enter that global minima. There is a problem. So learning rate too high is also a problem. Learning rate too low is also a problem. And that is how the hyperparameters work. We cannot set them to be too high, set them to be too low. We may have to discover them. We may have to spend some time on them, isn't it? You may have to discover based on the data that you have. Do you agree with that point? Let us see the impact of learning rate visually. Until now, I have explained the theory to you. Let me show you visually on the TensorFlow Playground. Then we will go to the Google Classroom Keras code file and check how learning rate is given. All of you go to TensorFlow Playground just to see visual impact of the learning rate. Playground, TensorFlow. Okay. All of you reach there and I'll give you the specifications. So the experiment that we are going to do here, is to understand the concept of learning rate. We want to understand the concept of learning rate. So in this experiment, there are 3 steps that we are going to follow. The first step will be, we will give learning rate as too high, maybe a very high number. Usually we don't do that. We will give learning rate as 10 or something. Can you make a guess what will happen in this case? What is the expected result if the learning rate is too high? If the learning rate is too high, what comes to your mind? You have to imagine that diagram that I have shown you. This kind of diagram. If the learning rate is too high, What will happen? We might even miss this global minima. That means our error will be, the weights will be oscillating from here to here. Error will not, reduce. Error will just stay stagnant after a particular epoch. That is what happens. What happens if the learning rate is too low? Very, very minuscule, maybe 0.00001. What comes to your mind first thing if the learning rate is too low? Tell me. If the learning rate is too low, what comes to your mind? You have to imagine that everything will move very slowly. The weights will be very slowly converging, errors will be converging very slowly. So there are two things that will happen. Slow convergence, agreed or not? Slow convergence. The other thing that may happen, what is the other thing that may happen? Yes, convergence will be slow. That is anyway understood. What is the other thing that may happen if the learning rate is too low? What comes to your mind? If the learning rate is too low, then you have to imagine this, right? This diagram. Then what will happen? We may get stuck in the local minima. Local minima issue is also there, and slow convergence if the learning rate is optimal. So these are the experiments that we are going to do. All of you ready on the playground? I'm going to give you the instructions now. Ready? So let us start the first experiment. Take the second data set. Take the second data set. I think this is XOR data, exclusive OR data. Ratio of training to test is 60%. Test data, how much, training data, how much. Noise means there are some points that are against the pattern, like usual noise, like choose that as 20 noise. Batch size, which I haven't explained until now, that is the next hyperparameter that we'll discuss. As of now, keep it 10 as it is. Take x1, x2, x1 square, x2 square. Take two hidden layers, 4 neurons each. 4 neurons means hidden nodes. Two hidden layers, 4 each. Are you with me, all of you? Choose the very high learning rate, 10, very high learning rate. And let us see what happens. We want to visualize everything so that we get a better understanding. Very high learning rate. Activation 10H, no regularization required. Okay? Are you with me, all of you? Have we covered everything? So with these configurations, you go ahead and execute this problem. Once again, I am setting second data set, 60% training to testing. Noise is 20. Noise is 20. Batch size 10. X1 square, X2 square. Two hidden layers of 4 neurons each. That is it. Learning rate very high. Highest number that is possible here in this particular app. 10H activation and all that. So what is expected if you execute like this? You can see this here as well. You can also execute in your system. If you start the execution, check this out. Error is beyond 100%. That means that there is something grossly wrong here. But what you would see is error is not at all reducing. Stop it, regenerate the sample, go to 0th epoch, restart. Check this out. Are you getting what I'm trying to say here? Error is not reducing. You like this learning rate is so high, the weights are rapidly changing so much that you are not able to enter. That means you are getting stuck here itself. Check this out. Let's say if the error function is like this, that's it, from here to here, here to here. Weights are moving from here to here. Error is that much only. Step size is too much. Stop it. Nothing will happen. Even if you execute for 1,000, 10,000 epochs also, nothing will happen. No improvement. Can you see what I'm trying to say here, all of you? That is the impact of very high learning rate. Let us see the impact of very low learning rate. Very low learning rate. Choose the same configuration without changing anything. Let us choose the least learning rate. Now tell me what is the impact that you're going to observe. What are you going to see here? If I choose the least learning rate, once again, tell me what comes to your mind. If I choose the least learning rate, very low learning rate, the convergence will be slower. You may get stuck in local minima. Check this out. It almost looks like you are going in slow motion. Until now, we haven't waited this much time for these two to converge, isn't it? They were very quickly converging. But now that learning rate is so low, weights are hardly changing from epoch to epoch. We have to wait a long duration. By now, we would have got the result within 1000 epochs. For all the other experiments, we got the results. This is the first time it is taking a lot of time. Why? Low learning rate, very low learning rate. It will converge. Maybe we may get stuck in a local minima as well. So very low learning rate is a problem. Very high learning rate is a problem. Let us keep executing like in the background. But you know what? What is the good news here? What is the good news? I know too high, very high learning rate is a problem. Very low learning rate is also a problem. But the good news is the optimal learning rate is not a single value, it is a range. If you are near to that range, you are through. You don't need to really worry about what exactly is the value that I have to set. Do I really need to spend a lot of time on discovering exactly that 0.003 or 0.03 is the optimal learning rate, and how much time shall I spend on finding this? Don't worry. If 0.03 is the optimal learning rate, maybe 0.001 to 0.05 until here, or maybe even till 0.05 until here. If you are near to that range, nearby the optimal value, you are through. So if you go back here, we have executed already 2200 epochs. It is still taking time. Check this out. Let us stop this. I think you got the point that I'm trying to convey here. What is the third experiment that we are going to do? We will choose some optimal learning rate. Luckily, if we are near to that range, then we are through. Let me choose maybe 0.03003. You can choose 0.01 or 0.03. Any of this. If you're near to the optimal one, then you are through. Let me choose this one and then try this out. Looks much better. Convergence faster, avoiding local minimas. Converging faster, avoiding the local minima. Check this out, all of you. Optimal learning rate. Once again, the point that I'm trying to make here is optimal learning rate. This is not exactly a single point. If you're near to that range, even if you choose 0.01 here, I'm just guessing. If you're near to that range, you are through. Let me just do this experiment with 0.01. Check this out. Working. 0.01 is also working. Stop this. Maybe slightly higher than that. 0.001. Earlier one is slightly lower than, now will slightly higher. If you are near to that range, you are through. Check this out. Yes, multiple solutions are possible. Optimal learning rate is not a single value that you need to worry about. If you are near to that range, then you are through. Okay. Looks like 0.001 is not a really good one compared to the other two options that we have tried. Maybe a slightly higher number is what I'll try. Maybe 0.03 is the one that we will try now. Or maybe zero point 0.1. Just for the experiment sake, I'm trying. Looks like 0.1 is also not a good number. So the optimal value is 0.03, somewhere 0.02, 0.01, 0.003. These are the ones that we can choose. That is the story of learning rate. This is what you have to keep it in your mind while you are working with deep neural networks learning rate. This is the visualization part of it. Now we will go to the third part. We are done with the theory. We are done with the visualization. We will now go to the part where we mention this learning rate in the code. This learning rate is mentioned in the optimization functions. We discussed this gradient descent optimization, right? So learning rate is part of this gradient descent optimization function. The internally that gradient descent optimization function is known as keras.optimizers. Internally it is known as stochastic gradient descent. The function name is SGD, stochastic gradient descent. I'll explain later on what is the stochastic part of it. As of now, you see this as gradient descent function. What do you mean by gradient descent function? Where does this name come from? If you take this as an error function, look at this, all of you. Where does the name come from? If you take this as the error function, at each point, what we are doing is we randomly start with some weights. We move in that direction where error is reducing. Error is reducing. You can imagine this as a kind of hills and valleys. Okay. You are moving in the steepest descent. To reach the ground, to reach the lowest point, you move in the direction where slope is reducing or negative, gradient descent. Okay, steepest descent. You want to move in that direction where error is reducing. How do you reach that point? By finding the gradient value and moving in the direction of the negative gradient, or moving in the direction where error is reducing. So that theoretical name is known as gradient descent. Here we roughly understood that as backpropagation algorithm, updating the weights. While updating the weights, I kept on saying we will move in the direction where error reduces. We will move in the direction where error reduces. That moving in the direction where error reduces is known as gradient descent function. Okay. Which direction, in which direction error reduces mathematically, if you calculate that using partial derivatives, that is known as gradient descent. This algorithm name is gradient descent. Mean that you give the learning rate. If you give a very high learning rate, you will see that accuracy kind of oscillating. It will never improve after a particular point. If you give a very low learning rate, what you will observe from epoch to epoch, hardly any change. If you give an optimal value, luckily the optimal value is not a single number, it is a range, then you will be somewhere here. Got it, everyone? Okay, open the code file, keep it for the execution. It is a pretty straightforward one. We will directly go to the code file, regularization run, activation done. So what we want to do is we want to do an experimentation on the learning rate. Here first I am defining the network learning rate 10, which is high learning rate very low, and then optimal learning rate. Okay. Let us do one thing. You select until here, activation functions is also done. Select until here and then runtime, run before, run anyway. After that, you do an experimentation on learning rate. While it is executing, I will now take the questions. Exactly the same way that we have discussed, you will observe that very high learning rate impact, very low learning rate, and then the optimal learning rate impact.